Okay, so let's start today class. Today we are going to discuss about this single phase full wave bridge type rectifier, uncontrolled rectifier. We maybe say that uncontrolled type rectifier for the resistive load. Okay, so just try to see there the circuit diagram and the output voltage waveform and current waveform and voltage across the diode. And after that, we try to the circuit simulate and observe their waveform in the simulation lab. Okay, so just first of all share the screen and then we will continue our discussion. Okay, so simulation of single phase full wave uncontrolled rectifier, bridge type rectifier for the resistive load. Okay, resistive load or R load. Why it is called uncontrolled rectifier? What is the basic difference between the uncontrolled and controlled rectifier? Okay, basically, this type of rectifier in uncontrolled type rectifier, we use such a power electronics switching devices which cannot be controllable. Okay, so we are not able to control the output voltage of the rectifier. That's why it is known as the uncontrolled. Okay, so as we know that the uncontrolled type power electronic switching devices, that means if you consider diode, okay, then whenever the diode are in forward bias, that means this diode start to conduction. You have no control about their conduction in this period. Whenever the diode becomes in forward bias, it just behave like a switching closed switching device, and the current will flow through this device. Okay, until and unless it becomes in reverse bias, diode continue to conduct. Okay, so we are not able to control the output voltage. That's why it is called uncontrolled bridge type rectifier. That means whatever the output voltage you got in such a power electronics devices of in rectifier, that means diode, whenever you, so output voltage is fixed. You cannot control this one. Output voltage V0 is indicated here, V0. And what is the difference in control rectifier? Okay, if we just select a overview about the control rectifier, that means we have to use such a power electronics devices which can be controllable their conduction mode. That means we are control the power electronic switches devices conduction period. That means if you use such like as a thyristor or other transistor family, okay, so we have to require to supply the gate pulse. Even in the thyristor in forward bias, they do not conduct until and unless we provide the gate pulse. Is it not? So whenever we provide gate pulse, from that instant, SCR or thyristor start for the conduction. that means we can say that for that through that gate pulse, we are able to control the conduction of the thyristor. So we are able to control the output voltage of the rectifier. So that rectifier we will discuss in another class. So that means by the using of such a power electronics devices, that means SCR. Okay, but here we just concern about the uncontrolled bridge type rectifier. So in a single phase full wave rectifier, first of all, just we try to elaborate the circuit diagram. So you may be familiar with this circuit diagram in power electronics also. So four diode, four diodes required for the bridge type rectifier. Okay, single phase full wave bridge type rectifier. We already seen in the previous class for the single phase half wave uncontrolled rectifier. That means only one diode required for the half wave. But here in single phase full wave, we require four diode for the bridge type rectifier. Okay. In single phase full wave, you may be use if center type rectifier, or we also call that midpoint rectifier, single phase full wave midpoint rectifier. For such rectifier, we required only two diode. But whenever we discuss about the bridge type rectifier, so minimum or that means number of diode required is 4. Okay, this is AC supply single phase voltage source. That means this is representation of the sinusoidal waveform of the supply voltage. That the voltage is instantaneous if you represent like such a small quantity. That means Vs, a small V suffix S. Okay, S for supply. That means this is your single phase AC source, and number of diode connecting in such a way that you may be number this diode 1, 3, 2, 4. Okay, 1, 3, 2, 4. Now you may be observed from this circuit in the positive half cycle. Okay, in the positive half cycle, the diode D1 and D2 in forward bias, because this positive terminal is connected to the anode of the diode 1, and negative polarity of the supply voltage is connected to the cathode of the diode 2. So in the positive half cycle, this diode D1 and D2 in forward bias. Okay, so you maybe know that the waveform of the sinusoidal voltage waveform, how we can draw from 1 cycle or 2 cycle. That means 0 to 2 pi. Okay, so from 0 to 2 pi, you may be draw the sinusoidal variation from 0 to pi in the positive half cycle and pi to 2 pi in the negative half cycle. Okay, so maximum magnitude you may be indicated through this sine wave, that is represent your, if you represent voltage, then that quantity of maximum represent the maximum voltage, or if you represent current, that means the maximum current. Okay, so in the positive half cycle, that means diode 1 and diode 2 are in forward bias. So diode 1 and diode 2 start to conduction from whatever, that means from 0 to pi. Okay, that means diode D1 and D2 are in forward bias from 0 to pi. Okay, so this is start to conduction. So you maybe find out the path of the current flowing through this voltage source to diode 1, and through this you will able to see the I output current, that means flow through the load, and again come back through this diode D2 to the negative polarity of the supply. Okay, so this is the path for the current in the positive half cycle, that means 0 to pi. Okay, you may be seen that from pi to 2 pi, that means in the negative half cycle. Okay, in the negative half cycle, so negative half cycle, the negative polarity of supply voltage is connected to the anode of the diode 3, and positive polarity of the supply voltage is connected to the cathode of diode D4. So in the negative half cycle, you may say that the diode 3 and diode 4 in forward bias. Okay, so it will try to conduct through this path, that means the current flowing through this path I D3, that means D3 D3 and through the load to again come back through D4 to the positive terminal of the supply. Okay, so this is the path for the positive half cycle and negative half cycle of the current flowing through the load, and this resistance is your load, purely load resistance, and voltage, whatever the voltage appears through this load terminal, that is known as the output voltage, and that will be indicated by V0. Okay, average output voltage, average output voltage indicated by V suffix 0. So this is the circuit, all about the circuit diagram of the single phase full wave uncontrolled rectifier. Okay. So now just we try to see their various waveform of the various component. That means the output voltage waveform, input voltage waveform, and voltage across the different diode, and output current waveform. Okay, so we just try to see that, and just after that we try to find out some parameters of the output. That means average output voltage, average output current, and RMS output voltage and RMS output current. Okay, so just we try to see here. That means, so it is all about the circuit diagram of the single phase full wave uncontrolled rectifier. Okay, now we just try to see there the waveform one by one. So yeah, so this is the supply voltage waveform. That means the Vs instantaneous value, you may be drawn such like a sinusoidal variation of the voltage. So for you may be draw for the one cycle, complete cycle, or two cycle. So this is your one complete cycle up to this point, and again from start from this point and again complete the another cycle up to this point. Okay, so here we draw sinusoidal voltage waveform variation for the two cycle. Okay, that means to from 0 to pi is your positive half cycle, and pi to 2 pi is negative half cycle. Okay, so this voltage waveform, that means VAB. Okay, it will be indicated by VAB, and opposite to that we how we can represent VAB equal to VA minus VB. Okay, if you want to draw the VBA, okay, if you want to draw the voltage of VBA, that means opposite to that one VBA, B to A. Okay, that means negative half cycle. So VB minus VA, this VB equal to VB minus VA. Okay, that means opposite of the VA. So if this waveform is indicated for the VAB instantaneous value of one complete cycle up to this point, and second cycle completed up to this point. Okay, so this is the VAB, and this one indicate the maximum voltage. VM represented by VM is your maximum voltage. At that means 0 to at 90 degree, you will get the maximum voltage of the supply voltage, that is represented by Vm, because we can represent instantaneous value of supply voltage Vs, small suffix Vs, equal to Vm sine omega t. Okay, Vm sine omega t. So whenever you put the value of omega t equal to 90 degree, you will get the sinusoidal value 1, that means maximum value. Okay, so you will get magnitude at that point, that is represented by Vm, that means maximum voltage. So at omega t equal to 90 degree, you will get the maximum uh, supply voltage, and at omega t equal to 0, that sine 0 is your 0. So you will get the supply instantaneous value is 0 at this point. After that, whenever you increase the omega t from 0 to 90 degree, okay, from 0 to 90 degree, you will get the supply instantaneous value increases corresponding to the angle of the sine wave, that means omega t equal to 30 degree at this point, omega equal to 40 degree, omega equal to 60 degree, and omega t equal to 90 degree at this point. And from this point, that means a 90 degree, again the supply input voltage try to decrease up to the point pi, up to the pi. Okay, so 90 to 180 degree, you will again decrease the same respective increases whatever take place from 0 to 90 degree. Okay, and again becomes to 0 at pi. Okay, and from pi to 2 pi, again repeat the same waveform, but in the negative half cycle. Okay, so again at this point, 180 plus 90, that means 270. At this 270 angle, you may be observe at this point. So you will get at this point a maximum negative voltage. That will be this one. You may be indicated if this one is your, at this point is your Vm positive. That means up to this point you will get the maximum Vm. Is it not? Maximum Vm up to this point. So this one is represented by maximum Vm at an angle of 270 degree. Okay. So we already explained their operating principle from 0 to pi, which diode conduct and how can current flow through the circuit, rectifier, and the through the load. Okay, and for the negative half cycle, that means during this period, that means voltage appear, that means VBA. So diode D3 and D4 conduct. Okay, so diode D3 and D4 conduct during this period pi to 2 pi. Okay, now we just try to draw the output voltage corresponding to that. Okay, we just try to draw the output voltage. As we already explained that the load is pure resistive. Okay, load is pure resistive. So just output voltage. We first try to draw the output voltage. So output voltage started from this point 0 to pi. Okay, so whatever the supply voltage waveform from 0 to pi, that will be appear from 0 to 2 pi, 0 to pi in the output voltage, and during this period diode D1 and D2 conduct. Okay, so same output voltage waveform you may be obtained whatever the voltage waveform of the input supply voltage from 0 to pi, is not. So this waveform is same here for the output voltage, that means VAB. Okay, and from this point pi to 2 pi, the voltage VAB, this one dotted line indicated here. So VBA you will obtain from pi to 2 pi. Okay, so you will be draw same as the this voltage, dotted line voltage, that means VBA from pi to 2 pi. So you will get the output voltage pi to 2 pi, such like this way. Okay, so again from this point the diode D1 and D2 becomes in forward bias. Okay, you may be seen from this waveform. So in the positive half cycle, that means from this period to this period, that means 2 pi to 3 pi, diode D1 and D2 again becomes in forward bias. So you will get the voltage VAB from 2 pi to 3 pi, and again same thing repeated from 3 pi to 4 pi, that means VBA. Okay, so this is the maximum voltage, whatever the maximum voltage of the input supply voltage that is represented by VMs. So this maximum voltage is also same. That means VM. Okay. So during this period, which diode is conducted, that means you have to keep in your mind. That means in 0 to pi, that means diode D1 and D2 in forward bias. So these two diode conduct from 0 to pi, is it not? And pi to 2 pi, diode D3 and D4 in forward bias. So this one will be conducted from pi to 2 pi. That I have also indicated here. That means during this period 0 to pi, that means D1 and D2 conduct, and pi to 2 pi, D3 and D4 conduct. Again, from 2 pi to 3 pi, D1 and D2 conduct, and 3 pi to 4 pi, D3 and D4 conduct. Now, next, we want to draw the voltage across the diode 1 and 2. Okay, we want to just draw voltage across the diode 1 and 2. That means this diode and this diode D1 and D2. Okay, so that means whenever the diode in conduction mode, we may be considered just like as a closed switch. Okay, that means you just path provide for the current flow through this way. That means just like as a switch is closed in conduction mode. Okay, so whenever the diode in forward bias, that means in conduction mode, so voltage across this diode will be 0, is not? That means anywhere the diode D1 and D2 conduct, that means the voltage appears across this diode is 0. So you may be draw their voltage waveform for the diode D1 and D2 and respectively for D3 and D4. Okay. So when diode D1 and D2 conduct, that means 0 to pi. So during 0 to pi, you will get the voltage across the diode D1 and D2 is 0. Okay. So you may be seen in the third waveform, that means voltage across the diode D1 and D2 from 0 to pi, anywhere the diode in forward bias, that means in conduction mode, so voltage across the diode D1 and D2 appear is 0. That means it's just like a closed switch. Okay, so sorted one, that means the voltage appears across the diode is 0. You know? So D1 to D2 is 0, and whenever the during this period, that means in negative half cycle. Okay, so this one, that means conduct current, that means your voltage is 0, and whenever the negative voltage appears across the D1 and D2 from pi to 2 pi, that means the same voltage of the negative half cycle of the supply voltage will appear across the D1 and D3. During this period, D3 and D4 conducted. Okay, so pi to 2 pi. D3 and D4 is conducted. So voltage across the D1 and D2 is your negative half cycle. Yes, that means in the reverse bias, these two diode becomes in reverse bias. So voltage appears of the negative half cycle from 2 pi to 2 pi. Is not. From this instant, again D1 and D2 becomes in forward bias. Is not. So VAB appear. That means voltage across the diode is 0, because during this period D1 and D2 is conduction mode. Okay. Again from 3 pi to 4 pi, the D1 and D2 becomes in reverse bias. That means appears the voltage of negative half cycle from 3 pi to 2 pi. During this period 3 pi to 2 pi, we already say that D3 and D4 in conduction mode. Okay. So now in the next step, we just try to find out the voltage waveform across the diode D3 and D4. Okay. So similarly, you maybe draw, that means D3 and D4, that means pi to 2 pi, D3 and D4 in reverse bias. So voltage appears of the negative half cycle from 0 to pi across the diode D3 and D4. Okay. But pi to 2 pi, the D3 and D4 in conduction mode, here we already say that. So whenever the diode in conduction mode, that means voltage appears across those diode becomes zero. So you may be observed from this dark line, that means pi to 2 pi, you will get the voltage across the diode D3 and D4 zero, you know. And again from 2 pi to 3 pi, the D3 and D4 in reverse bias, because during this period D1 and D2 becomes in forward bias, so this one is conducted. That means the across the D3 and D4 from 2 pi to 3 pi becomes the negative half cycle of the voltage of supply voltage. That means negative half cycle can shown here. And from 3 pi to 2 pi, D3 and D4 conduct. So voltage across the D3 and D4 it becomes zero during 3 pi to 4 pi. Is it not? So from 3 pi to 4 pi, it becomes 0. So this is all about the waveform of the various component involved in the single phase full wave uncontrolled type rectifier. One more waveform we can draw here for the output voltage waveform. Okay, one more waveform. So that means output current waveform. Okay, so we already explained that consider that for the pure resistive load circuit. Okay, that means whatever the voltage waveform is same as the current waveform for the resistive load. Is not same waveform follow the current current waveform. That means voltage divided by resistance. So you will get the current waveform. That means you may be draw the output current waveform from 0 to pi. That means this is similar to the voltage output voltage waveform. That means this one, and again pi to 2 pi, this one. So output current doesn't change for the purely resistive circuit. Okay, so you may be draw here if I have not shown. That means this one you may be drawn below to this one, this waveform. That means same as output current. So from 0 to pi is similar to this output voltage waveform, and pi to 2 pi same things. So because we maybe first of all, why it is called the single phase full wave uncontrolled rectifier? Because we are not able to control the output voltage. We already explained that. And in complete one cycle, you will get the output voltage for the full cycle. You may be compare the output voltage waveform from the half wave. So in one complete cycle, you will get only output voltage for the half cycle. That means up to this waveform, and from this point to this point you will get zero. Okay, so here the output voltage waveform will be obtained for the complete one cycle. That's why it is called the full wave rectifier. Sorry, it's not full wave rectifier. So that means output voltage we can improve by using the single phase full wave rectifier compared to the single phase half wave rectifier. That we try to show here by driving the equation of the average output voltage for the single phase full wave rectifier. We already drive the average output voltage for the single phase half wave rectifier also. Okay, so you may be compare from the output voltage equation of the single phase half wave rectifier and single phase full wave rectifier after the derivation of average output voltage for single phase full wave rectifier. That means you are able to see that the two equation, that means single phase full wave average output voltage is double of the single phase half wave rectifier. We already here we obtained that the two, that means for the complete one cycle we will get the output voltage. So obvious that whatever the output voltage we have obtained, average output voltage for the single phase half wave rectifier, so here that will be double obviously. Okay, so we just try to find out by the derivation also. Okay, so you can now draw all the waveform of the single phase full wave uncontrolled rectifier. That means supply input voltage, output voltage waveform, output current waveform, and voltage across the diode D1 and D2, and voltage across the diode D3 and D4. Okay. So now we just try to find out the average output voltage of the single phase full wave rectifier. So this is our output voltage waveform. So if you remember that how we can find the average output voltage of any waveform, okay, that will be standard formula, that is nothing but if you represent by uh, x t function of t, then 1 by t average output voltage x0 equal to, we can write 1 by time period 0 to time period xt dt. Okay, 0 to time period xt dt. Okay, so you maybe put on that a standard formula of this waveform. So here the, what is the time period? What is the time period for this waveform? Okay, what is the time period? You maybe repeat it from this point to this point same. So you need to consider that 1 by pi here is your time period. Okay, so just put on that a standard formula. Now that means 1 by time period 0 to time period xt dt. Okay, so average output voltage, that means a V written here for the voltage, because we are going to find the average output voltage value. Okay, so average output voltage value V0 equal to 1 by time period. That means 1 by pi. The time period for this waveform is pi, and integration from 0 to time period, that means 0 to pi, and a Vt dt. That means Vt equal to here, what is Vm sine omega t and d omega t. Okay. Now you just integrate this sin omega t d omega t and put their lower limit and upper limit, you will get the average output voltage value. Okay, average output voltage value. So you maybe take this Vm as the constant, because this one is constant term, so you can take outside of this integration. So in the next step you can write here Vm by pi integration from 0 to pi Vm sin omega t d omega t. Okay, so what is the integration of sin omega t? If you know that, you can just put here their integration value of sin omega t, and after that you will just put their lower limit and upper limit and just simplify the equation. Okay, so sin omega t equal to uh, minus cos omega t, and after that you just put their lower and upper limit of 0 and pi. Okay, so this one in the next step you can write here Vm by pi integration of sin omega t equal to minus cos omega t, lower limit is 0 and upper limit is your pi. So just put here, so cos pi is your minus 1, so minus minus plus 1, and again minus minus plus put the lower limit, that means cos 0. So cos 0 is your value 1. Okay, so minus cos pi, that means minus minus plus 1, and cos 0 is your 1. So Vm by pi into 1 plus 1, that means 2 Vm by pi. Okay, 2 Vm by pi. So average output voltage for the single phase full wave uncontrolled rectifier is your 2 Vm by pi. Okay, if you compare from the single phase half wave uncontrolled rectifier, then you, I think, obtain their value Vm by pi. Okay, so that means here double the average output from the single phase half wave. Okay, so if single phase half wave and control rectifier value was Vm by pi, so we obtain here for the full wave rectifier 2 Vm by pi, is not 2 Vm by pi. Now we just try to find out the average output current. If you want to find out the average output current, so you already find out the average output voltage, that means V0. So just put here the value of V0 by R. Okay, so average output current, that means maybe represent here average output current I0 equal to V0 by R. So put here the value of V0 equal to 2 Vm by pi into already R here. So average output current value is 2 Vm by pi R. Is not average output current value is how much? 2 Vm by pi r. Now, how we can find out the RMS value of the output voltage? How we can find out the RMS value of output voltage? So, if you know the standard formula for the RMS value of output voltage of any waveform, that means you maybe, I think, remember that if that one indicated by RMS value of any waveform, that means X suffix RMS equal to 1 by time period 0 to time period x square t dt whole to the power 1 by 2. Okay, so this is the standard formula for the RMS of any waveform. So you already find out the output waveform time period here, that means pi, and just put here the value of x square t. That means here we just write here sine square omega t. You know, sine square omega t. So just put on that standard formula. That means 1 by time period 0 to time period Vm square sine omega t d omega t whole to the power 1 by 2. Whole to the power 1 by 2. Okay, whole to the power 1 by 2. Now 1 by pi 0 to pi Vm square sine square omega t whole to the power 1 by 2. So just we can take outside of this Vm square and 1 by root 2, 1 by 2, that means Vm. So we can take outside Vm. So we can take here outside of the this square under root Vm. So remaining part is just right here 1 by pi. Okay, 1 by pi. We can just write sine square omega t. We are not able to directly integrate. So just convert the sine square omega t in terms of cos sinusoidal. So we can write here 1 minus cos 2 omega t divided by 2, that is equal to sine square omega t. Is not. We are not able to integrate sine square omega t directly. So just try to convert in sine cosinusoidal form. That means 1 minus cos 2 omega t divided by 2. So just 2 take already outside here. And here just 0 to pi 1 minus cos 2 omega t d omega t whole to the power 1 by 2. Is not. Now you just integrate this one and put the lower limit and upper limit. That means whenever you integrate this one d omega t, this for this one, and minus integration of cos 2 omega t d omega t. So this first term you may be write omega t. That means put here the value of lower and upper limit, that means pi minus 0. So this first term becomes pi. Is it not? First term becomes pi. And the second term, that means minus integration of 0 to pi cos 2 omega t. So this one becomes the sinusoidal form, sine 2 omega t divided by 2. Okay. So this in sine omega t, if you put the value of pi and 2 pi, you will get the value of 0. So second terms you will get 0. Is it not? Because the sinusoidal value of at pi and 0 will 0. So second term you will get the 0. Only you obtain for the first term, that is pi. Okay. So pi from the numerator and denominator is cancel out. So only 1 by 2 whole to the power 1 by 2 remains after the simplification or integration of this bracket part. Okay. So what is the overall value of V output RMS? That is V maximum by root 2, because 1 by 2 whole to the power 1 by 2, we can write root 2. Okay. So RMS output voltage for the single phase half wave, single phase full wave uncontrolled rectifier is V maximum by root 2. Okay. V maximum by root 2. V maximum by root 2. Now you can just find out the RMS value of output current V output RMS by resistance. So V maximum by root 2 into R is your RMS output current. Similarly, you may be derive the equation power delivered to the load V output RMS I output RMS That means here an input volt ampere Vs supply voltage into I output RMS. So input power factor you maybe also find out that is equal to 1 for the single phase full wave control rectifier. Okay, so this is all about the single phase full wave uncontrolled rectifier for the resistive load, their operating principle, waveform, circuit diagram, and the average output voltage and other parameters. That means RMS output voltage and RMS output current. Okay, so in the next session, we just try to simulate the circuit in the MATLAB and try to observe whatever we explained here the waveform. Okay, so just please stop here and the next session.